Welcome. Nice that you are here. My name is Petra Pouwels. I'm a colleague of Joost Kuijer, who you met yesterday and this morning. And today I'll try to give you some insight into a very nice method in MRI, which is called diffusion. Please ask questions during my presentation if something is not clear. So after this hour or 1.5 hours, you will be able to explain what all these images, what they mean and how you can interpret them. So that's challenging, but let's start. Diffusion, in fact, it's not a very nice, good word, but it's called Brownian motion. You've probably heard of that during physics class in high school. I hope you did. But of course, you all know that if you have a drop of ink and you put it in a glass of water, if you wait long enough, the whole ink will be distributed over the glass of water. And that's because all the water molecules, they are all diffusing or all doing a Brownian motion. So they push towards the ink molecules, and at some point the ink is distributed over the glass. So the water molecules and the ink as well, they show what we call Brownian motion, and we want to express it in a magnitude. So we want to say what is the distance that the molecules move over a certain amount of time. What are factors that influence the distance of the molecules? Yeah, temperature, that's a very good one. A lower temperature is going faster, or is the distance longer or smaller? Yeah, slower. Yeah. If I have a cup of hot tea or hot water, the diffusion, the sugar is dissolved much faster than if I have a glass of ice. So temperature is one. Other, maybe if I don't have water but another fluid. Yeah, viscosity. Yeah, that's a very good one. So the viscosity also determines how this Brownian motion takes place. But typically we are looking at the brain or the rest of the body, and that's mainly water and not so much oil or other substances. So, but what happens when I have this glass of water, but I put in a few spoons of couscous or macaroni? What happens then with this? The distance that the molecules can move in a certain time. You have any idea? Will they make easy a longer distance or rather a shorter distance? Shorter? And why? Yeah, but it's mainly because they have barriers. So the water molecules are still water molecules, but the water molecules may want to, travel, say, for 3 or 4 steps. But now, there's a couscous molecule. So there are membranes or barriers which hinder the diffusion of the water molecules. Yeah, it's not about solubility, so it's not about that the couscous can solve, but you just have the water, and then the water can go everywhere, because there's until it gets until the edge of the glass. But within the water, the molecules can move around freely. But if you have these macaroni or couscous molecules, then they touch upon strange structures. So the distance that the water molecules can travel, they are bounced back, and on the average they have a smaller distance. That's clear? So, and then what we call the diffusion is then reduced or restricted. So when we plot this in a graph like this, here on the x-axis is kind of the mean time, and on the y-axis is the mean distance. And if we have a short time, then of course the distance is small, but if you have a longer time, then the distance becomes longer. So for instance, in free water, so in the glass of water, which we can also say that CSF, the cerebrospinal fluid, is just like water. The molecules have a certain freedom of diffusivity, and it's shown here by this line. But what happens when we put in the couscous or the macaroni, which is of course in the brain, will be just brain tissue, then at the same time the distance is shorter. So this red line is less steep because the molecules can only travel over a much shorter distance. So here there's CSF, and this is the tissue, approximated by the couscous or by the macaroni. So the strength or how fast this diffusion is, we call it the diffusion coefficient or the diffusivity, and in the diffusion is hindered, the smaller diffusion coefficient, because we do have these barriers, which is the brain tissue, the membranes, the cells, etc. And of course in CSF, typically the temperature is about 37 degrees, so in the CSF the diffusion is also faster than in a glass of cold water. But if I have hot water, then the diffusion is faster again. Sorry, how? How do I define? That will be in the next slide. Yeah, but finally, it's the richtingscoefficient, the steepness of this curve. So if this is a steep curve, so it's about the time and the total distance that molecules can travel. Yeah, it's not speed. Speed is something like millimeter square per second. But this is the overall. In a second, it's about certain. It's not really speed, and it's also not flow. So it's not. I mean, speed, that will be, for instance, if your CSF is flowing, that's really a certain speed. But here it's random. It can be in any direction. Potential speed? No, I don't know that one. You can find it if you look at diffusion coefficient, Brownian motion. You can go further into that. Yeah, that's too far for this lecture. Oh, how can we measure it? Well, actually, it's quite funny because we measure something in a very short microstructure scale, because we are getting measures in micrometers, but in MRI we are looking at much bigger voxels, but we'll come back to that later. We do have a T2-weighted sequence. You don't have to know much about that, but I'll just... Of course you know about a T2-weighted image. You've heard that from Joost. So this is a T2-weighted image, and you can get it with a normal T2-weighted sequence. Well, what are we doing when we do diffusion measurements? We add certain what we call gradients. We call it diffusion sensitizing gradients, and we also express that with a certain B value. It's about the strength of the diffusion. I show it here in this orange blobs. And when I do that, my image becomes much darker. Well, why is that? Well, first about this diffusion sensitizing gradients. A gradient in MRI is an additional magnetic field which varies with position. Typically you have one magnetic field. What is the typical field strength that you can measure? What is, if I measure a clinical scan, typically I have two field strengths that I can choose. 1.5 Tesla is one, and the other one is 3 Tesla. So these are typically certain magnetic field strengths. But then, in principle, the whole area in this magnet is 3 Tesla or it's 1.5 Tesla. What are we doing with the gradients? We add an additional small magnetic field, but not a constant, so it's not 3 and everywhere a little bit 0.1, but it's depending on position, we add a certain extra magnetic field. And we indicated it with these colors. So depending on the position X, Y, or Z, we have an additional field strength, so the external magnetic field is B0, and we add a little bit extra. So these gradients are played here during these orange times. And first we are looking at a molecule which is fixed. So it's a water molecule which is, say, in a cage and it cannot move at all. This water molecule, so the position is constant and it remains constant during this whole sequence. So it means that spins, the water spins, the proton spins, they feel always the same magnetic field. So some may be feeling the purple one, but they're feeling the purple one, purple field strength during the whole time, so both here and both here, and actually it doesn't matter. So they, as if nothing happens, and there's actually no effect of these gradients. Now we're getting to a mobile water molecule. This molecule moves through space during this pulse sequence. It means that maybe during this first gradient, it is at the yellow part, so it experiences a certain magnetic field, V0 plus yellow, but it's moving, and maybe in the second part it has it as the blue field strength. So the field strength before and after or during this whole pulse sequence is changing. Well, why exactly? It's a bit too far, but just believe me, then the signal is reduced. So you keep the same signal when the field strength remains the same, so either both times the yellow or both times the purple one, but if the field strength is changed during this whole sequence because the molecules are moving, then you are losing signal. So the most important thing then to remember is that a mobile water molecule, which can be diffusing, for instance, through the CSF or the extracellular space, so these water molecules, they feel different fields during this first and the second gradient, and we get signal loss. And then the signal loss is larger when the diffusion is faster, or when the molecules move more easily, or when the gradients are stronger. Yeah? That's the first gradient is this one, and the second gradient is that one. Yeah? So if they are identical, so they feel they are at the same position, then nothing happens. But if they are moving, then they lose their signal. Oh, these are RF pulses, yeah. This is a 90-degree RF pulse and a 180-degree RF pulse. Yeah, that's correct. So, can you see this screen? So, the diffusion is faster. That is a tissue property. So, it's either you have CSF, where the diffusion is really fast, or you have tissue, where you have restriction, because you have couscous or macaroni barriers. And the second one is when the gradients are stronger. That's a scanner parameter. So I can adjust on the scanner whether I want these orange gradients bigger or larger. The big one, that's the external field strength. So we have an external field strength of 3 Tesla, and we add a little bit. And we add a little bit, but this, especially the addition, depends on position. That's the whole idea. When I would add, again, only purple everywhere, I would just have 3 plus a little bit everywhere. But because I add this gradient depending on position, therefore I can measure this effect of the diffusion. And these same colors of the gradients, you will learn about that tomorrow by a lecture by Joost. I don't think he mentioned it already yesterday. Did you have anything about gradients? Okay, then tomorrow there will be another gradient. Yeah, why gradients are used in MR. I think I have only one slide with kind of an equation. You don't have to remember it completely. But what we measure, so that's to come back to how can you measure the diffusion coefficient? Well, we do have a signal intensity. We measure it so after our pulse sequence, and the signal intensity is the signal intensity 0, so when I don't have a gradient, and it's multiplied by exponent of minus b times d. Now this minus b is the b value, it's the strength of the diffusion weighting. You don't have to remember all of this, but it's about the gradient amplitude, so it's about the height of this diffusion gradient and about the length of this diffusion gradient, and also between the timing between the two. And that's a scanner parameter. So I say to the scanner, use this b value, and then something is happening. We also have this d, the diffusion coefficient, and that's a tissue property. So this d, or the diffusion or apparent diffusion coefficient, we have several names for the same thing. This defines the diffusivity, or actually the mobility, of a water molecule. So this SI0 is the signal intensity without gradients, and the SI with a certain b value is when I add gradients. And switching of gradients, so adding this additional magnetic field, that makes the noise in an MR scanner. So you probably all know that MR scanners make noise. They always make noise because of this, what Joost is going to tell tomorrow. But with diffusion, we add additional gradients, and especially those are very loud. So you really need ear protection if you are in the scanner and you do a diffusion-weighted imaging. How do the images look like? Well, first of all, for diffusion imaging, we always need what we call this reference image. So we always need to have the image without b values. That's called b0, no diffusion gradient. And that's shown here in this example. This is the T2 weighted image, but it's with b equals 0. Then we do have, in this case, two different b values, one at 500 and one at 1000, and they are all scaled at the same scale. And you see that you lose signal very rapidly. And when I now put a region of interest here in the CSF, here in the ventricles, this blue one, you see that in this graph I have the B0, the B on the x-axis, and I have the signal intensity on the y-axis. And I start with a very small b value of about 0, and I have a high signal in the CSF. This is also because I have a high T2 relaxation time. That means that my signal intensity of CSF is very high in a T2 weighted image. So I have a high signal. But then when I go to the B500 or to the B1000, at B1000 it's almost completely gone. So you see here 3 points at 500 and at 1000, and at 1000 it's almost 0. And then I go to the white matter, an area here. I have this red region of interest. I start with a much smaller signal intensity because the T2 relaxation time of white matter is shorter than of the CSF. So I start lower, but you see I also lose signal, but it's at a much lower pace, and even at 1000 I have even higher signal in the white matter than I have in the CSF here. Well, I can do an exponential fit through these points, and then I get my what I call diffusion coefficient, or apparent diffusion coefficient. For the CSF, this is about 3 times 10 to the minus 3, and for the white matter, this is about 0.9. So this is a much slower, and this is a faster diffusion. And of course, the CSF again is water-like, so it's you can understand why the CSF has a higher diffusion coefficient than the white matter. And of course, I can do that just voxel by voxel. Here I have just an ROI, but for every voxel, every pixel in these pictures, I can measure my ADC. So I get an ADC map, and that's shown here. So I start with high signal here in the CSF, but a very low signal in the diffusion-weighted images. And then the ADC is high in the CSF, and the ADC in the white matter and the gray matter is much lower. Well, how can I calculate this? Well, again, I had this equation. You don't have to completely remember, but you can have this changing and your equations, and from this you can have the diffusion coefficient. It's 1 over b times the log of the signal intensity at b divided by the signal intensity of b0. The apparent diffusion coefficient is approximately the distance that molecules can travel in a certain time. So that's what I started with in the glass of water, the diffusion coefficient of the diffusivity, or the ADC. We have a lot of names which actually mean the same. So the distance that molecules can travel in a certain time, and we call it here the apparent diffusion coefficient. It's kind of the average. I'll come back to that in the second part of the lecture. But so the diffusion coefficient, or the apparent diffusion coefficient, the diffusivity, that's all the same. And in CSF, it's higher than in the tissue. Eve was first. Yeah. How can we use it? I have a few examples in pathologies, and they are being shown in the next slides. Yeah? Oh, yeah, it's a very good question. So this ADC, that is already based on B0 and B500 and B1000. So the steepness of this curve is this ADC. So the ADC doesn't have, I mean, it should be the same. If I have only the B0 and the B500, I would be able to calculate ADC. If I have only B0 or the B1000, I would be able to calculate the ADC. But it's just based on, you can see here the D, or the ADC, is just an 1 over B times, yeah, the ratio of these two signal intensities. Why? Well, it's nice to have an image. If I would do it here, I only have two values because I have a region of interest with, say, the mean intensity. But if I have the image, I can immediately see in the image whether things are high or low or different. So I'll, again, in the pathology cases, you will probably see it as well. Yeah? I think you first. Yeah, just to repeat, it's not put together, but it's, if you have the B0 and the B500 and the B1000, you can calculate the ADC. But the ADC itself is not, and that's also, I mean, you start with a high signal here and you end up with a low signal there, which means that the ADC is a very steep curve. So the ADC is the fitting through these points. It's you cannot, if I have just, but I can calculate it from it. But it's not the average, I mean, because the B values itself, the signal intensity doesn't give any information, but the computation using these images gives the ADC. But I call it yeah. And it's easier for radiologists to look at images, because then you can, and I mean it's the same because every voxel here corresponds to the same voxel here, and I can. Yeah, I hope you also had still a question. Or no, sorry, you had a question. Sorry. Yeah. Gradients. Yeah, yeah. Well, I still get signal from water. So if I have a small B0, this is still a normal image. But I get, so you would say, okay, I have not so nice images with a higher B value. What can I learn from it? Well, you can learn it using the ADC, and again, I hope that the examples in the next slides will give you a bit idea why you would do this. And if not, ask me again. Then we go back to this one. So first, to have an idea what happens during development. Not even going to the ADC. Of course, I will come back to the ADC in the next slide. But first, I have here pictures of a child, a very young child still, 10 months old. And what kind of image is this one? Does somebody know that? T1. It's a T1 weighted, and how do you see that? At least we do see high signal intensity of the white matter and a grayer of the gray matter, and that's what we see in a T1 weighted image. And we use something that such as we don't see indeed the CSF. That's clear. And what type of image is this? By now you should know that because I've shown T2. This is a T2 weighted image where you see high signal intensity in the CSF, and you see also some contrast in this case between gray matter and white matter. Not so much yet because it's a very young child. But this same child was also scanned at a much earlier time point at the age of 10 days. And well, then you say, oh, what image is this? Well, again, this is the T2 weighted image. And again, you recognize it at the CSF signal. And this is the T1 weighted image. But you see that the contrast here in this very young child, here the white matter is gray, and the gray matter is even white brighter. And also here, the contrast is almost completely reversed to that of a T2 weighted image. What is the main thing during development in the first couple of months? What changes in the brain? I'm looking for one phrase, one substance. Any one of you know? We do have axons in the brain. I mean, a child can have something, but what is around the axons? Myelin. So myelin or myelination, a very young child, a just born baby, has only very little myelin around the axons, but the axons are there, and of course there are still a lot of other things needed to be done, but the myelination is something which occurs during the first couple of months. And this myelin very much influences the actual T1 and T2 relaxation times. So that's why if you have actually the same kind of scanner settings, that you see a completely different image here than compared to at the age of 10 months. And of course here still it's not yet completely myelinated and it's still continuing, but here you see big changes. It's a very good question. Indeed, and I'll just repeat it that they can also hear it. If you have Alzheimer's disease or MS, where you have demyelination, whether you have an image which I see here on the left, but not completely, because there's not complete demyelination, but indeed in the MS lesions, so in the areas which have really what we call acute demyelination, then you definitely see that, well, you get these lesions you can see on the image. It's not exactly like this, but indeed, because the myelin is changed, we do see changes. And not only on the images, but also again on the ADC, because that's why I show these images. So here, first of all, you see that there are big differences here, and the same differences we also see in the ADC. First, I show here a child at the age of 1 year and 7 months. And again, you see here on the left the B0 image. So this is the T2 weighted signal image. There, this is the diffusion weighted, so with a higher gradient with the B1000. And you see that indeed in the CSF you start with high signal, but at and in the diffusion weighted image it's gone. And this is the calculated ADC. Well, you've also seen those images. But what happens now in a neonate? This in a very young child. Again, the T2 weighted image looks completely different, just as I showed you before, because of the difference. And then I have this B1000, the diffusion weighted image. Well, that looks quite similar again. But then when I calculate the ADC from these two images, then again I see a big difference. Of course, in the CSF, it's approximately the same. I mean, this is just fluid, and doesn't matter whether it's fluid in a baby or fluid in an older child. But you see in the white matter, but also in the gray matter, the ADC is much higher, because it's still, the brain is so, fluid-like that the molecules can move around easily, so the ADC is higher in a normal neonatal brain than in a normal adult or older child. And what you also maybe see in this child, you hardly see any difference in the white or the gray matter. So approximately, so the average diffusion or the apparent diffusion coefficient in white and gray matter is approximately similar. In the baby, in a neonate, you do see some changes, because especially the white matter is more fluid-like. And it's always very good to compare the signal intensity, for instance, in the ADC map with that of the CSF, because then you say, oh yeah, it's brighter, so it's more diffusion. Yeah. 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 Yes. You don't put in the scanner anything, because you only calculate this one from these two. So the ADC, you cannot say to the scanner, make me an ADC map. Yeah, you can do it, but first you have to make this one and that one, and then the person can go out of the scanner, and on your computer you say, I want an ADC map. Yeah. So you don't say, I only want ADC. You can only have an ADC map if you have those two. And also you cannot have only one. You always need the B0 as well, or a second one as well. Yeah? No, indeed. It's not T1 weighted, not T2 weighted. It's just a measure of actually kind of the ratio between the B0 and the B1000. So then one small question, what's the difference between B0, a small one, small b, and the capital B0? Yeah. So the small B0 stands for the strength of the gradients, which is absent then, because it's B0. And the capital B0 means the external field strength. And indeed, because you asked for it, which is a very good question, how can you measure, or what kind of image is then the ADC? ADC is only a calculated map from those other, and actually this ADC is a quantitative value. So the gray level here has really a meaning, and it can be compared between subjects. So in this subject I have an ADC. Well, I didn't put on the numbers here, but I can really have a number for the ADC, and here I have a number for the ADC. Of course, I can also have a gray level here, but a gray level itself doesn't say anything. It can be 500, it can be 0.5, it can be 500,000. It doesn't mean anything, but the ADC, because it's based on two different or two images, which has been done in the same measurement, of course, I can calculate this ADC, and it's an absolute value. Oh, gray level is if I have here a bright signal, I have a hyper intense signal, so a high gray level, or high is more white, and if it's black, it's a low level. So it's just, yeah, you can, if you see in the workshop tomorrow, you can see what is the signal intensity. So signal intensity is also gray level. So if it's bright, it has a high gray level, and if it's dark, it has a low gray level. But it's just an arbitrary unit, and the ADC is not the arbitrary unit, but it's really an absolute value. So now to the pathology. I think I have 2 examples of it. Well, you probably will recognize this is in a neonate. I do have here a B0, or the T2-weighted image. You've seen on the left, and well, if you look carefully, you probably do see that something is weird here in this occipital area. Here is the B1000, or the diffusion-weighted image. Well, you immediately will recognize this large, bright, or high gray level in this area. And then when I calculate the ADC from these two, from the B0 and the B1000, I have an ADC which is shown here. Well, this is apparently not healthy. What happens here? Here was the one of the arteries was completely occluded, which means that there's not enough oxygen and fresh blood is going to that area. We see a high signal intensity on the diffusion-weighted image here, and we also see a low ADC value calculated from here to there. We can calculate the ADC, and the ADC is very low here. Again, you see in this frontal area of the white matter, you see again the high high ADC in the white matter, which you saw on the previous slide. This is normal, but here in the occipital part and in the thalamus, it's clearly abnormal. What happens here? Well, there was not enough oxygen and fresh blood delivered to this area, which leads to a failure of the sodium-potassium pump. And this sodium-potassium pump is used for or having a good normal situation with osmosis and particles crossing the membrane. And in this case, the water can only remains in the cell, and the cells are really swelling. And this is something that we call cytotoxic edema. And the cells are swelling. Well, just see it as I had the couscous, and I just wait a long time, and the couscous is all swollen, and there's hardly any water left. Or if you have the macaroni and you put it on and cook it, and you didn't put enough water in, then oh, my water is gone. So the whole extracellular space between the cells is gone. So it means that the water, or there is of course still a little bit of water, but these water molecules, they can hardly move anymore. They are actually kind of become static molecules, as if they are fixed in this cage and they cannot move around anymore. So the water remains in this smaller extracellular space, and we have what we call restricted diffusion here. You can argue that also the intracellular space becomes larger because the cells are swollen, but here the diffusion is already much lower because we do have cell organelles and all this stuff. So typically what we see in images is signal of the extracellular space or of the CSF, and the extracellular space is completely reduced in this case. That's why we see this. Then another example of pathology, not in a neonate but in an adult brain. Again, we have a B0 image, T2-weighted signal here. You see already a little bit strange here on this occipital or parietal area. We do have B1000, the diffusion-weighted image. And again, you see a very bright area, but also another bright area around it. And then we do have the ADC, which is again calculated from the B0 and the B1000. And the ADC looks like this. So we do have, normal brain, which is here in the front, which is normal brain. We do have a core of the tumor, which is shown here. In the T2, it's dark, okay. In the B1000, it's very bright. And when we calculate again from B0 and B1000, we get an ADC which is very low. What means a low ADC? Can the water molecules diffuse freely, or are they restricted? They're restricted. And that's because in a core of the tumor, when there's a very high cellularity, so there are lots of cells growing, so the cellularity is so high that the water molecules can hardly move anymore. So in this case, we start with maybe a lower signal, but it's really restricted and the ADC is low. So we do have a ADC low because of restricted diffusion. We also have a surrounding area here. You see, it has already quite some signal on the T2 because it has a high T2 relaxation time. It's already a little bit more water. This is called what we call normal edema. Not cytotoxic edema, but say normal edema. On the diffusion-weighted image, I also see quite a high signal, but if I calculate based on B0 and B1000 the ADC, I clearly see that the ADC is quite high, so the water is indeed quite freely to move. So, and also please note, if you only look at only look at the diffusion-weighted image, you see, of course, this core, but you also see the surroundings, and you can say, oh, that's a quite high signal on this diffusion-weighted image. But you always need to take into account this B0, because if the signal is already high here, then the resulting ADC can still be high here. So you still need both data. To the next part, because diffusion, I didn't tell anything about 2D or 3D, but in fact it is 3D. I had the example of the macaroni, but what happens when I put in spaghetti in a glass of water? Is there any preference, or can the water move around the spaghetti in this direction as easy as in that direction? No, and which one is easier? Which direction?
Well, if the spaghetti is this way, I assume the water will move this way.
Oh, okay.
Or no, actually following the spaghetti.
Okay, yeah. Yeah, and of course it's not the spaghetti itself. I mean, it's the water between the spaghetti. Actually, there's too much spaghetti in this glass. There should be much less spaghetti because we do have still a lot of water here, and the water can more easily, move around in that direction, in the length direction of the spaghetti, than perpendicular to it. Everyone agrees with that? Good. So why spaghetti? This is an electron microscopic picture of the optic nerve, and this is the longitudinal section, and this is the transverse section. And again, we do have this optic nerve. And what is this again around this optic nerve? Myelin. So there's a lot of myelin around the axons here, and the diffusivity along, and we call it here axial diffusivity with this symbol, is easy along the nerve, and it's much more difficult, or the distance that the molecules can travel is much smaller when it's perpendicular to this nerve. So this diffusion, again, we call it anisotropic in things like white matter. We do have the axons and the myelin, and the parallel or the axial diffusivity is relatively unhindered parallel to the axons. Do I still have a mouse? Mouse. Yeah. It's relatively unhindered parallel to the axons, but it's very strongly hindered perpendicular to the axons, to the nerve direction. And we do have again a lot of different names, L1 or L23, axial diffusivity, radial diffusivity. Sorry about that. how can we measure this with MRI? Well, again, we use these gradients, but you can also, this diffusion gradients, we can play out in different directions. So we can have a gradient in the x direction, so from left to right or from right to left. So I can have this, say, the low value at my left ear and the high value at my right ear, but I can also have it from my nose to the back of my head or from top to bottom, but also any combination of it. So it doesn't have to be exactly 3 directions, but I can play out my gradients in all different directions. And if I play the gradients in different directions, these are all diffusion-weighted images, so with, say, the B value of 1000, but in different directions. So here I have this structure. This is called the posterior limb of the internal capsule. This is a structure where my corticospinal tract, so my motor tract from my motor cortex to my spinal cord goes, and this goes through this small area here, which is shown here in white. In this case, the gradient is perpendicular to this fiber, but in this case, my gradient is more or less parallel to this actual fiber. So depending on the exact direction of my gradient, I have a high signal here in the corpus callosum, or I have a low signal in the corpus callosum. And of course, I don't need to calculate that all by myself. That's done by the computer. And we do have what we call a tensor. I just noted here on the blackboard that there was also vectors and matrices here. I don't know if you have, it was not your lecture probably. Well, for diffusion, the tensor, it is a matrix with 9 parameters. And to calculate this tensor, I need at least 6 gradient directions. So not just x, y, and z, but also 3 orthogonal and preferably even more. But I don't need to calculate that myself. That's done by the computer. It's important that the amount of signal loss depends on the actual gradient direction that I used. But it means that for each gradient direction, I need a different image. And not just the image that I showed just one slice, but the whole brain, of course. Well, a brain volume, which I mean here, say 40 slices, 40 actual slices, this is what I call one brain volume, needs to be done with a B0. I always need my reference. And then with 6 different B1000. And again, all B1000, but with different gradient directions. So this is the minimum that I need, which is here 1 B0 and 6 high B values. In clinical practice, I rather have a little bit more, for instance, 2 of the B0, 12 high B values, or even much more combination of B0 and different high B directions. But it means that we need to scan the brain multiple times, not just one T2-weighted image, not just one diffusion-weighted image, but 6 diffusion-weighted images or 12 diffusion-weighted images. So we need a very fast sequence. I don't want 5 minutes, B0, 5 minutes, certain direction, 5 minutes, because then the patient has already left the scanner before I'm finished. This fast sequence, we use a technique which is called echoplanar imaging. Did Joost mention echoplanar imaging? Maybe not, no. Maybe tomorrow he will tell it, but just remember the name. You don't need to know exactly why and how, but this name is important. The voxels that I typically use for this sequence is probably 2 by 2 by 2 millimeters, so every voxel has 2 millimeter length, or even larger, 2.5 millimeter. What is a typical voxel size of a nice T1 weighted structural scan? How big are the voxels there? Ten micrometers, 100 micrometers, 1 millimeter, 5 millimeter, approximately. 5 millimeter, 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 No idea? Oh, typically 1 millimeter when in what I call a 3D sequence, so a three-dimensional sequence where all my voxels are the same size, so where in all directions, then I typically have 1 by 1 by 1 millimeter. That's nice. Then I have a good, what we call spatial resolution. But it takes about 5 minutes, 4 or 5 minutes for this scan. So again, we do want a faster scan here, and also because we want it faster, we go to a little bit more ugly images. So they're not that nice, but good enough. So again, the fast method, and here we use only about 10 to 20 seconds per volume. So I have maybe only 10 seconds the B0, 10 seconds a certain direction, 10 seconds the other direction. So then within 2 minutes, I can have really a scan with different B1000 directions. These images are not so nice as regular anatomical images. But in total, the regular anatomical images, they take maybe 3 to 5 minutes, and they have much smaller voxels, 1 by 1 by 1, maybe 0.9 by 0.9, or maybe 1.2 by 1.2, but approximately that size. So how do these images look like? Well, here I have the B0. Here at 3 different orientations, I make the images typically transverse, so axial in this direction, so from top to bottom or from the bottom to the top. And that's shown here on the right image. Here. But with my software, I can immediately see how they look in the 3 other directions. So in the sagittal orientation or in the coronal orientation, and here, so where the cursor is in the green lines, you see all the different directions. So this is the B0, and then I have a B1000 shown here. This is in, say, direction 1. Here is direction 2, and at least 6 or more, or 30 or 24 directions. So I have different images with different diffusion directions. Well, maybe you already noticed there are some weird areas here in this area just above the eyes and also near the eyes. And this is what we call geometric distortion. This very fast sequence is nice, is fast, but it also has some disadvantages. And that is what we call artifacts. And these are the artifacts that we have with this EPI. We call it susceptibility artifacts. They occur especially near interfaces or between air and tissue. So where tissue is surrounded by tissue is no problem, but when we have tissue and then air and then bone, we can have problems. And you can see it here in this brain. You can see it here in the skull base, or near the ear canals, or just above the eyes. And you can also see it here, what we call a phantom. This is just a bowl of water with very nice structures in it. A normal scan of this phantom looks like this, but in the EPI you see that I have a clear distortion. And also in the normal. And also when I look at this one, which should have a nice rectangular grid, you see that it's completely distorted and you do have very strange things. Well, fortunately, we can kind of check that and of course control for it. This is the distorted scan, and then I can also correct it. So again, this is this distorted one, and the corrected one looks nice. So it's good to know, but also know that we can have distorted images. Then we did this all the directions, 6 directions at a high B value, or 12 or 14, and I can reconstruct different maps again from it. Just as I could reconstruct my ADC map from the B0 and the B1000, I can reconstruct different maps from my diffusion tensor. And of course, I still have my T2 weighted or the B0. Well, you know about this, you recognize this. I can also say, okay, I have all these different orientations, but I can kind of average those. And then I can, what I call the isotropically or diffusion-weighted image. And this is also the image that you already know. I can still calculate my ADC, my apparent diffusion coefficient, which is again kind of the average over all the directions. But now I have another contrast, and I call this the fractional anisotropy, or FA. And well, what you can see here, this is all of an adult. I don't have examples of a child in this case. But in the ADC map, you see that the white matter and the gray matter have approximately the same apparent diffusion coefficient. So the average diffusion of water doesn't matter whether it's in white matter or in gray matter. But what happens now in the FA? I do see a high signal intensity here in this area, in the corpus callosum, and over here. Is this FA higher in the white matter or higher in the gray matter? So is it brighter in white matter or is it brighter in gray matter? What is a typical white matter if I say the corpus callosum? You still know what it is? This is the bridge between the two hemispheres. Is that? That's white matter. Yeah, that's white matter. So there's a lot of myelin. These are actually, when I should have made an image here with spaghetti and macaroni. The white matter is all spaghetti. So they have all a certain direction, and the gray matter, the cells at the edge, they're all gray matter. That's all the macaroni. So the white matter I see here as a bright. This is here, and it's over here. And the surroundings, the gray matter, is all lower FA, lower anisotropy. The FA comes. No, I think my presentation is correct for your answering your questions, because I hope I can explain it here. So typically, from the diffusion tensor that I calculate, I extract two different maps. Typically this ADC, well, it is the trace of the tensor. You don't have to remember that. But you should know that I can extract the ADC from it, but also the FA, and this depends both kind of a not exact ratio, but it depends on how the parallel diffusivity or the axial diffusivity and the perpendicular diffusivity. And I can visualize it as follows with an ellipsoid. In this case, I have isotropic diffusion, so my parallel and my perpendicular diffusivity are the same. So if I put it in a ball, it's really a very nice round ball, and the green, I don't hope you are colorblind. This is green, sorry, and this is red. The green has the same value as the red ones, so this is a nice ball. And the FA, the anisotropy, is 0. So it's very isotropic, so it means that all the diffusion in all directions is the same. I cannot make any distinction. And the FA is 0. Then I have, for instance, a kind of a rugby ball, what I call mild anisotropy. And here I do have a certain preference for the parallel or the axial diffusivity, the green one. And the FA, or the perpendicular one, is a bit smaller. Maybe I have an FA value of about 2. And then I also have this more cigar-shaped stuff, where I have what I call strong anisotropy. So here my parallel diffusivity or axial diffusivity is very high compared to the perpendicular diffusivity, and here my FA is higher. In fact, my FA can be maximal 1. That's really the highest value, and the lowest value is 0. So it can be between 0 and 1, and it says something about this form. Well, you can imagine that this one should be about CSF. There's no preference. The gray matter has some preference. I mean, their cells have some structure, but it's not that much. And white matter has really a clear structure with spaghetti like this. Yeah. If the red one becomes bigger, yeah, actually you could have what we call pumpkin. So that we do have two red ones and a small green one. You can have that we call crossing fibers, and I'll come back to that in a minute. No, it's not negative. It will be smaller because it's it can only be between 0 and 1. But the idea of say 0 for the CSF, and the more cigar-shaped it is, the more spaghetti-like. So this is water, this is macaroni, and this is spaghetti. So we do have again this FA. You see it here again. So FA is here. I do have again this ADC. And sorry about that, we also can call it mean diffusivity. It's the same as ADC. And we also have the two different compartments. So actually the green and the red one that I showed before, this parallel or the axial diffusivity and the radial diffusivity, they again have different patterns. But typically in clinical practice, we mainly use the FA and this ADC. But I only show these as well. Until now, I only showed it in gray levels. So again, the gray levels is the FA. If it's high, it's bright. The FA is say 0.8 or 0.9. If it's dark, it's 0.0 or 0.1. It's a gray level. But I know exactly the direction that my scanner, that my gradients were played out. So instead of only knowing that I have a certain preference, I also can see what is the direction of my preference of diffusion. And some smart guys thought about this color system. Again, you should not be colorblind. I don't know what people do if they are, because then it's difficult. But this picture is meant for an actual image, so shown here. So you do see here in the center, you do see a big red part, and this red means left-right. So what is again this structure that is shown here in red? As shown here also in red, and shown here in red? The corpus callosum. So the real bridge between the left and the right hemisphere, the corpus callosum, is, of course, left-right. And of course, you still also can see a little bit here, left, right, more in the other areas, but this is the real big red area is here. Then we do have green, which is in the actual slice more from the anterior to the posterior, or from posterior to anterior. And you see here green colors. Yeah? ADC says about the overall diffusion and whether it's restricted diffusion or more easy diffusion, and FA tells something about how much preference there is for a certain direction. And that's in gray levels, and if I go to the color levels, then I even know in what direction the main diffusion is. But back to this green one, can anyone think of a white matter bundle which is going from front to the back? Where are my eyes? In front of my head. Where is my visual cortex? Occipital, in the occipital head. So when my visual cortex should be about here, my eyes are about here, so it's very nice if they can communicate with each other, because the input of my eyes should go to the visual cortex. So there are fiber bundles which really go from the front of my head to the back of my head. So the green ones here, of course there are even more from front to back, but definitely also the visual tract is going from my eyes to the visual cortex. So that's what is in green. And then I also have here the blue one. In the axial slice, it's shown as going into the image. So then we go again to this, what I call the, do I have my mouse? Yeah, this is the posterior limb of the internal capsule, but I also can see it here. Where's my motor cortex? And where does the signal from my motor cortex go? And how? So what fiber bundle, what big tract is going from top to bottom? Yeah, what something like? Yeah, I have a spinal cord, but this is the corticospinal tract. So from the motor, or the motor tract from my motor cortex to my spinal cord must go from top to bottom, and all the other way around, my sensory tract. So if I touch my finger, also here the signals have to go from there to my sensory motor area, which is just behind my motor tract. So it also goes from the bottom to the top. When I say from left to right or from right to left, it doesn't mean that it has a certain, I don't know exactly the direction. So it's not like the blood flows, of course, through a certain vein or goes back through the veins. It has a certain direction. The diffusion of water doesn't have, I don't know which direction they go. So it's just about, it's a highway that's present. So the corpus callosum is a highway with axons and myelin around it, and the water can, move on that highway, but I don't know in which direction, because it's just random. It's just random motion of water. It's still Brownian motion, and it's not flow. It's not blood flow. It's not CSF flow. It's not water flow, but it's just water motion. So left to right doesn't mean from left to right, but only to indicate where the path is. So using these colors can also be used for what we call tractography. And how can we do tractography? Well, again, you see these FA images, the actual one and the coronal and the sagittal one. And on these color, or not, in this case, not the color images, but the gray level images, I can put small directions with the main direction. So is the cigar in that direction? Yeah, in which area is it? Is it going? Of course, I have to zoom in a little bit, otherwise you don't see it. Oh. And here you can see, again, we do have the corpus callosum here. We do have the corticospinal tract here. And you see here in the corpus callosum, you nicely see that, you kind of can follow the main direction. And for instance, if I start at a certain voxel here, I can follow it, and probably my fiber tract will go like shown here in the yellow curve. And when I do that for all the voxels, I can get things like this. And in these graphs, you see again all the fibers, but they're also shown here in the same color indication. So in blue is again the fibers going mainly from top to bottom, and in red from left to right, and in green from anterior to posterior. Well, if I show that now in 2D, because it's difficult to do it in 3D, you can think, okay, if I start here in this voxel, I'll probably have to go over there, and it's not so likely that I go in that direction, because, well, this is easier. This is what we call deterministic tractography. Every time that I start here, I will end up here. So each pixel or each voxel has one fiber direction. But again, what was approximately the spatial resolution of my diffusion-weighted images? So how big were the voxels? Two by two by two approximately, yeah. How big is an axon with myelin around it? Or how many axons with myelin will fit into a 2 by 2 by 2 voxel. Hundreds, thousands, a lot. I don't know exactly how many, but not just 2 or 3, but really hundreds. This means that if I look at that voxel here, it can also be that this red direction, which is the main direction, is just the resultant of 2 other directions. So then I come mainly to your question about the green and reddish colors. If I have a fiber like this, which is very nice, but if they're all together like this, I have still the same. They are parallel, which is nice. So the FA of this one is 0.8, but it remains 0.8 if all fibers in one pixel are the same. But what happens when I have fibers going in this direction and I do have other fibers that are crossing in a completely different direction? The main FA will probably be smaller, because I had a nice cigar shape, but now I pressed it together in what we call a pumpkin, and the FA will be lower. But it means that if I know that, it can happen that this voxel is not, check it again, it's not mainly that direction, but is maybe the resultant of 2 crossing directions. Well, using more advanced computer stuff, I can also do probabilistic tractography, and it means that I can say, it will be in that direction, but there is also a chance that this voxel is definitely the resultant of 2 crossing fibers. And you can see that actually already in your FA maps. Again, the same FA map as before. The voxels is about 2 by 2 by 2. If I look at areas where my fibers are really running nicely parallel, so in this cortical spinal tract or in the corpus callosum, then indeed I have a high FA, and I see that also on a bright on my FA map. So the parallel tracts, they have a high FA. But when I look at here the green arrow, my FA is much lower, and that's mainly because I do have crossing tracts in that voxel. And then automatically my FA will be a little bit lower. And that's why probabilistic tractography is nice. And that's actually also the reason why, if I do have images like this, in fact, I forgot about I didn't put it in because I didn't want it to have much longer. But in MS, you can see that the FA is lower or the ADC is higher in a lesion because the myelin is gone there, and also the FA is then reduced. But if I look here in healthy people, I also see these bands, kind of stripes, where the FA is much lower. And it doesn't mean that the myelin is damaged there. But when I look at the color maps, you clearly see that exactly in these areas where I do have a lower FA, that's exactly where the fibers that going from top to bottom, the cortical spinal tracts, they really pass the tracts that go from the front to the back. So in these voxels, I do have just a combination of different orientations, and that's why my FA is lower. Again, with this graph. Well, how can I do that in practice? How can I do this tractography? You see here, in a single subject, I have the motor cortex indicated here in blue. I know that the cortical spinal tract is going through the cerebral peduncle, which is also a structure. I can also indicate it here in green, and I can do what we call probabilistic tractography, and that's shown here in red and yellow. And in yellow is that they say, okay, this is a very high probability that my tract is going here. And in red, maybe a little bit lower probability. Maybe the tracts are also going a little bit to the other side. But I can get something like the probability of my cortical spinal tract in this subject in these three orientations. And when I can do that in one subject, I can also combine different people together. Of course, I have to make sure that all the data are in the same space, so in the same atlas space or whatever. That's too far for now, but I can, so that's why I call it a standard space. But then I also can say, okay, my cortical spinal tract probably goes from top to bottom, which is of course clear. And in this case, I have in light blue, it's a high probability, so maybe 9 of 10 subjects have the cortical spinal tract over there. And if it's a bit darker, then maybe not all subjects, but most subjects also have it over there. It's set here. So tractography for a single subject, we can often do it with what we call the deterministic tractography, which is very nice for the major tract, so the cortical spinal tract. I can easily do that with deterministic tractography. But if I want to have more precise determination, I often do this with probabilistic. And then I can see not only the major, but also the minor tracts. Take-home messages, well, everything of course. But to kind of summarize, you should know that with simple diffusion-weighted imaging, we use diffusion gradients and we actually average them over all three directions. We always need a reference image, which is typically always a T2-weighted image, and we have diffusion-weighted images, for instance with a B1000 or a B750 or a B1200, and based on the B0 and the high B value, we calculate the ADC. Then we have advanced diffusion-weighted imaging, which we also call, or in 3D, which we call DTI. Then we need diffusion gradients along at least 6 gradient directions. Again, we need reference images and at least those. And from the diffusion tensor, we can calculate again the ADC, but in this case also the FA. And the FA, you know, it has a certain color. We can have the direction, and it can be used for fiber tracking or tractography. That's the same. And it's nice if you understand whether and why the ADC or the FA differ between white matter, gray matter, and CSF. That's always good to know. And also know a little bit about the effect of development, but also on a different few pathologies what they have on ADC and probably on the FA.